Today we're looking at complex zeros and a fundamental theorem of algebra. So we've looked at zeros before. We've talked about rational zeros, how to find the rational zeros. And we've answered this question, how many zeros does the polynomial have? So by looking at the polynomial, we would see our largest exponent, which would tell us our degree. It's a degree 2. So we could at most 2 real zeros. So then I would want to find what those zeros are and figure out if they actually are all real, rational, irrational, imaginary. So by looking at this, first thing I would do is try and factor. It's not factorable. So then I would use my quadratic formula, negative b plus and minus square root of b squared minus 4ac all over 2a. Okay, so if we simplify this, this is going to get us negative 2 plus and minus the square root of negative 16 all over 2. Taking this a step further, I can see if I simplify that square root, I would get 4i, because you can't have a negative under the square root, it's an imaginary number. And simplifying this down, we are going to find we have the answer, negative 1 plus and minus 2i. Meaning we do in fact have 2 roots, but they're not real, they're not rational, they're not irrational, but these type of roots are what's called non-real, or we could say imaginary roots. So looking at this fundamental theorem, it says if we have a polynomial function of degree n, we can say it has at most n complex zeros. Complex meaning both real and non-real. So our total number of zeros will equal the degree. Some of those zeros could be repeated. All real numbers are also considered complex numbers. That's something you want to keep in mind. So whatever the degree is, in short, whatever the degree is going to equal the number of zeros, complex zeros that that function will have. We had stated before it would have at most the degree, but now we are going to say, well, in total, it will have whatever the degree is. That's the number of zeros it will have, just some will be real and some will be non-real. So looking at this one, how many zeros would this function have? Well, again, we would have said to begin with, at most 5 real zeros. But now looking at this, we can say it's going to have, in fact, 5 total zeros. So that's taking into account real and non-real, or real and imaginary. So I went to the calculator, graphed it out, and this is what that function looks like. And we can see the zeros. We can see that it crosses at 3 real rational zeros, negative 2, 1, and 4. But from that theorem that we just had, the theorem says we have to have a total of 5 zeros. So we can at least say, well, we have 3 real zeros. Okay? And those zeros we know are going to be negative 2, 1, and 4. So what that's telling us then is we have 2 non-real zeros that are left over. And we're going to find those on our last question of this video. We're actually going to figure out how to determine those zeros. But something to kind of keep in mind, if they are non-real zeros, and even if we take a look back at the graph, that means they're not crossing the x-axis, which means they're not x-intercepts. So that's going to be huge. So while they are zeros, if they are non-real, they are not x-intercepts, which means they will not be on the x-axis. So you're not going to see them. So they may be there, but you may not see them. Okay. So once we get our zeros, this linear factorization theorem basically says we can take all of those factors, and I should be able to either determine the zeros, and that should tell me all of the zeros, The only issue here is some of them are maybe not necessarily distinct numbers. So again, some may be repeated zeros. But we should be able to at least take a look at those linear factors and say those factors are going to help determine my zeros. Okay, so from this information below, we had this previous, and we said this was all true for all real rational zeros. Now it's going to change though when we get to the complex case, and we set up above, the one thing that is not going to be true is it's not an x-intercept of the graph. Everything else remains true with a complex zero. It is a solution, it is a zero, it's just complex, and I can say x minus that value will still be a factor. The only thing we lose here is it's not an x-intercept. So we're going to look at this polynomial function. Notice the type of zeros that we have here, and we're going to identify the zeros of the function and the x-intercepts of its graph. So looking at this, if I took each of the factors and set them equal to 0, that would tell me what the zeros of the function are. 1 0 we have is x equals 5. 1 0 we have is going to be x equals the square root of 2i. I is on the outside. The other one we're going to have is x equals negative square root of 2i. Okay, so keeping in mind x equals 5, this is a real zero. We could also say that this is a rational zero, where these are going to be imaginary. Or we could say non-real zeros. The x-intercept will only come from our real zeros. So we could say we have an x-intercept of 5, which would give us that coordinate 5, 0. Now, they want us to write this function in standard form. In other words, they want us to expand this out. So suggestions I would have would be work with perhaps that imaginary section first to expand it out. The reason I say that is because that is going to be the product of difference of two squares, So when we multiply that together, you're going to see that middle term is going to drop out. So our first terms give us x squared. Your outside terms and inside terms are the same thing. One's positive, one's negative, so that drops out and cancels. And then we just have to be careful here. So a negative times a positive is a negative. Square root of 2i times square root of 2i. I'm just going to write this as square root of 2i squared for right now. Okay? So simplifying this a little bit, when you square something here, remember it's like multiplying it by itself. So the square root of 2 times the square root of 2 is the square root of 4, which is really 2 simplified. I squared is just that, it's I squared. But our I values, we want to keep in mind, I squared is equal to negative 1. So right now, if I were to simplify that, that's a negative 1. So this factor turns out to be x squared. If I have a negative 2 times a negative 1, that gets me positive 2. Okay. Expanding this a little bit more and simplifying, we are going to find in standard form, we will get the function x cubed minus 5x squared plus 2x minus 10. So here's standard form. We have 3 zeros. We see that 1 is a real zero at x equals 5. We have 2 that are imaginary, or we could say non-real zeros at the square root of 2i and negative square root of 2i. So these two things that we just took a look at, these are going to be considered conjugates of each other. One is a positive, one is a negative. And this complex conjugate zeros here, something to consider and keep in mind. So if we have a polynomial function with real coefficients, it says a plus bi is a 0. Its complex conjugate, so notice a plus bi and a minus bi, those are those conjugates, is also a 0. Okay, so we are going to check out what happens and see. It says we're going to use substitution to verify that 2i and negative I are zeros of this function. And it says, are the conjugates also zeros? So one thing I want you to keep in mind with this function here is notice what we have. We have a complex coefficient, different from most of the other functions. So to kind of speed this up a little bit, I used my calculator, and in our graph section, I typed in our equations. So you can see that is going to be the second function that we're going to take a look at in question 2, and f2 is going to be this first function that we're looking at. So rather than evaluating it and doing the algebra, I used my calculator, and I went back into my calculator and I typed in my function, and it wanted us to evaluate it at 2i. So when I evaluate the function at 2i, I get a 0. That's good. We're trying to show and verify it's a 0. When I evaluate that function at negative I also get a 0. But now it says, are the conjugates 2i and negative I also zeros? So if I look, 2i here, when I plug that in, well, now I'm getting an answer of negative 4, not a 0. When I plug in the other conjugate, which is I, I'm going to see also not a 0. I'm getting a 2. So back to our notes, we have verified, we showed by using our calculator that those, when we did that f of 2i, we got a 0. And when we did f of negative I, we also got a 0. But when we plugged in f of the conjugate being negative 2i, we ended up getting negative 4. And when we plugged in f of the conjugate, which is I, we got 2. So are they also zeros? Nope, they're not. Okay. We did the same thing with this next function. So again, notice this function here, this next function, plugged it in. This is going to be in my calculator, f3. And again, notice I have over here a complex number. So when we are evaluating and showing it as a 0, I can see f of 3, when I plug in the 0i, gives me a 0. When I plug in the 0, 1 minus I, it also gives me a 0. Now, when I keep going down and I plug this in, I can see when I plug in the conjugate, I am not getting a 0. When I plug in negative I get 2i. I can see that is not going to give me an actual solution. So I cannot say, again, the conjugates are going to be zeros. What I can tell you is noticing the differences that we have here. Okay, so I can say, nope, that's not going to be a 0. The conjugate, so f of I, that's a 0. We saw f of 1 minus I, that's a 0. The conjugates are not zeros. Okay, when we evaluated the conjugate, we said f of negative I, well, that became 2i. And when we evaluated f of 1 plus I, well, that also became 2i. So a conclusion that you can draw, if you have your complex conjugate theorem, it doesn't work necessarily or hold true for polynomial functions with complex coefficients. So I can say your complex conjugate theorem doesn't necessarily hold true for complex coefficients. Okay. So on the back, we're going to write a polynomial function of minimum degree. So that means just think about them as 1 0 each, meaning I don't have to worry about repeated zeros. And it says in standard form with real coefficients. So now we can use that complex conjugate theorem. Meaning, I know I have a 0 as x equaling 3, negative 3. I have a 0 at x equaling 4, and I have a 0 at x equaling 2 minus I. But because I know it has real coefficients, that means we get its conjugate as well. So even though it's not stated as a 0, complex conjugate theorem implies that it is in fact a 0. So we want to write this as a polynomial. In other words, we're going to try and figure out what that function would look like. So I'm going to write each of these as factors. So if my 0 is negative 3, the factor is x plus 3. If my 0 is positive 4, the factor is x minus 4. Now, be careful when doing these. It's always x minus your 0. Same thing over here. X minus your 0. And now it's just going to be a matter of expanding and simplifying. And again, kind of like we did before, I would probably group them, do my real numbers together and do my non-real numbers together. So if I expand out the real numbers, this one isn't too bad, just doing a little distribution here. It's going to turn out to be x squared minus 12x minus 12. For this, I would say be careful. I would probably first step distribute my negative on both of these so I can see what's going on, and so my signs are clear. And then I would work through and distribute to each term. So I would work from right to left, distribute my x to all of them, go back, do the same thing with the negative 2, and then go back and do the same thing with the I. So keep in mind we still have this first polynomial. Expanding this out, we're going to have x squared minus 2x minus ix, next term, starting with negative 2, negative 2x plus 4 plus 2I. Now we're on our last term, distributing that I through. So I have plus ix minus 2I minus I squared. That's a lot. But the nice thing is most of this should drop out. And if I take a look, I have a positive and a negative ix. Those go away. I have a positive 2I and a negative 2I. Those go away. I know my I squared is equal to negative 1, so keep in mind this is a negative, negative 1. This is really plus 1. And if you've done it correctly, all of your I terms should drop out. Now we just have to simplify. So simplifying, we have x squared minus 4x plus 5. And over here, x squared minus x minus 12. And then the very last thing that you have to do is same kind of thing like we did up above. Distribute through. Distribute and then combine like terms. So start maybe with your x squared, work that in, go back, do the negative x, and then on the very last step, go back and do the 5. I'm going to leave that algebra for you to try. I will give you your final answer. Hopefully when you do that algebra, you're going to get it to work out. Be careful with your signs. Be careful with combining terms. So now that's that polynomial in standard form. The very last thing is going to be to answer that question that we had on the front page. What are the zeros of the function? So we used our calculator and we were able to say we had a 0 at negative 2, we had a 0 at 1, and we had a 0 at 4. We knew that there were 2 other zeros since it's a degree 5. It's just that they were imaginary. So the way we are going to do this is with synthetic division. I'm going to pick a 0, and I'm going to start to divide this out for each 0. So doing synthetic division, knowing it's a 0, keep in mind, your remainder should be a 0 when you're done. So we get a negative 10 here, add that up, I get a negative 5, multiply by negative 2, I get a positive 10, add that up, I get a positive 4, multiply through, I get a negative 8 with a remainder of 0. Okay, now I'm going to use this answer and I'm going to divide out my next 0. So I'm not even going to rewrite this. I know that I'm just using all of this information from up above. I'm just going to be careful with my work. I'm going to bring down the 1. So 1 times 1 is 1, plus a negative 5, I get a negative 4. Negative 4 times 1, I get a negative 4, and I add, I get a positive 1. Multiply, I get a 1, add, I get a negative 4. Negative 4 times 1, I get a negative 4, and add, I get a 0, which again should happen because it was a 0. Now the last one that we have is 4. Again, we're going to keep our answer, keep dividing out what you have. So I'm going to bring down the 1, I get a 4, I add, I get a 0. I add here, I get a 1. I add here and I get a 0. So now I'm done. I've divided out all of my real zeros. But keep in mind what this really represents right now. So this is giving us x squared plus 1. That's our other factor that we have. So if I took x squared plus 1 and I set that equal to 0 to solve, I'm going to be able to find those other imaginary answers. And keep in mind, when you square root, you get both a positive and a negative value. So we have a negative 1 under the radical. So that is telling you you have plus and minus I. These are your non-real zeros or your imaginary zeros, and we have 2 of them. Up above, we found these zeros. These are our real zeros. These are our rational zeros. We have 3 of them, and that's giving us our 5 total zeros. Now, if we were to write this finally in its linear factorization, all that is saying is take all of those zeros that we have and write them as factors. So our 1 0 is negative 2. That means the factor would be plus 2. We have a 0 of 1. That means the factor would be negative 1. We have a 0 of positive 4. That means the factor is negative 4. And then don't forget your imaginary zeros. So we would have x minus I, and we would have x plus I. So the idea here is we're working with complex zeros. We will practice more of this in class. Hopefully this gave you at least a good foundation so that in class we can kind of solidify these concepts.